So to continue where we left off, as you saw, the electrons, these wires, must lead you to go into the light bulb, through the filament, and back out, back to the battery. So what ended up working, some ideas that worked, right, was you then connecting your battery, directly putting your light bulb on the battery and taking your wire and going around like this. What I wanted you to notice as well is that wire didn't have to end there. You could have extra wire leading out. And the electrons will come out of the negative, go through here, go into the side, up through the filament, back out the bottom into where the positives are. So if you bypass that and you allow this wire to connect directly into here, that is our short circuit. And that's what was causing a lot of your batteries to become warm. So what I would like to do now is to put some definitions to what we saw here. So I said that the battery acts as a pump and separates electrons from the protons. The wires are simply there to direct, right? Just like the pipes take water to your house or a higher level. The wires do the same thing over here. Wires direct electrons to where you want them. So just like over here, as the water falls, it causes the wheel to spin. I drew the light bulb like this so you can picture these electrons as they fall down to get back to the protons. They will light the light bulb. So what we say is the separation of these electrons and protons causes there to be electrical potential. Over here with our water, when you lift the water up, you have what's called gravitational potential. So in our electrical potential, the electrons have the ability to do something when they fall back down to the lower potential level. With water, when you raise it up to a higher level, they have a gravitational potential energy that when they fall, that energy goes into something else. So it's a very similar concept. I like to use the water because it gives you a good visual of that. We will often reflect back on that. But for now, what I want you to understand are some terms that we are going to use. Capital V stands for voltage, measured in units of volts. This is the battery. Okay. The voltage source acts as a pump to raise the electrical potential energy of the electrons. Next, we will have current. The electrical current, just like water current, is the flow of those electrons. We symbol with a capital I, or the variable used to represent it is a capital I. Current is measured in units of amperes. Oops. Or amps. Okay, I current, amperes or amps. So current is the flow of electrical charge. It is the number of coulombs per time period. Going through a cross-sectional area, right? So if I had, here's my wire, and here's all these electrons passing through that wire, literally what the current is I'm counting how many of these electrons pass through per second. So the number that can go through, of course, is dependent on the cross-sectional area of the wires and also that voltage. How much am I pushing the electrical current through? So we have voltage, current, and the bulb, or whatever I use in my electrical circuit, is known as the resistance, R. Measured in units of ohms, symbolized with the Greek letter omega. And resistance is the opposition to the flow of current. This, because it opposes it, uses the electrical energy of the charges. So it's going to use up that energy. So in each circuit, to be complete, right, we have our power source, we have our resistor that's going to use up the energy, we have the wires that carry that electrical current. So some other terms that I want you to be familiar with is simply the word circuit. Means a complete, well, shouldn't say complete. Circuit simply means a pathway. Right? If we have a closed circuit, we have a complete pathway with no gaps. If we have an open circuit, you have a pathway that contains gaps. And this would be the biggest difference between an electrical circuit and a water circuit. In an electrical circuit, I can't have a gap. If I have a gap anywhere, even if it's over here, those electrons will not flow because they're not going to go through the air to get back to the positives. So it's not like they would go through the light bulb and make it work and sit out here and wait. They aren't going to go at all. Whereas in a water wheel, no matter where I have the opening, water will still flow. It may not get to where I want it to go, but it will come out of the pipes. Whereas with electricity, if you have a gap anywhere, nothing will flow. So in your water wheel, you put in a faucet or something like that, right? That you can turn the water on and off. The other difference is the water literally will sit and wait there for you to create that open circuit with the faucet. So if you were to break the pipes right here, you would have water in there up to the faucet. There may not be any after that, but it would sit there and wait. Whereas over here in our electrical circuits, when we put in our switches, so something like this, the electricity will not sit there and wait to go through. It'll actually not be anywhere in that circuit, not even in these wires that are right after the battery. So it's not like they sit there and wait to go. So those are a couple differences, visuals to have different between our water circuit and our electrical circuit. Now, as you can see here, these are some drawings that are maybe difficult to do to keep drawing our light bulb, our battery, our wires. So the last thing I want you to take notes on is symbols. So we're going to draw what we call circuit diagrams. And to do that, we are going to use circuit symbols. So the first symbol, as we see, everything needs is a battery. Right? So our battery is going to look like this. The long end of that is your positive. The short end is your negative. and everything gets connected from that battery with these wires that are going vertical. If you want to connect multiple batteries together, you would go positive, negative. That's considered a cell of batteries. So you would just keep drawing them until you go off. And as you see, you must have a negative on one side and a positive on another for the electrons to flow. So this would be considered a cell of batteries with a certain amount of voltage. Typically, you just draw a battery and you label how much voltage you want that battery to be, but that's our symbol for a battery. A wire, just a straight line. If you have wires that are crossed and they are supposed to be electrically connected, you put a little dot there. If you have wires that you want to cross, but you do not want them touching one another, you would draw something like this. So this is insulated wires crossing. So you do something to insulate them from one another. Make sure that there is no connection. Have a light bulb, right? So our symbol for a light bulb is just what it looks like with a squiggly line in between. Sometimes you might see them drawn with a symbol like that. That is simply a light bulb. Sometimes we have things in our circuit that are not a light specifically, but could be something else that's using up the energy, or its only purpose is to use up the energy. And this is our resistors. And finally, what we'll often use is a switch. And as I just drew previously, that's our symbol for our switch. So the purpose of the switch is to create an open and closed circuit. So if I wanted to draw this, which we built in class, in circuit form, in diagram form, I would draw my battery, positive side, negative side. The wires came around. Here's my light bulb. I left my light bulb, went back to my battery. So that would be a circuit diagram of the circuit that we built today in class with our light bulb. So it does not have to be built like this, but it has to be connected like that. So just as you put that light bulb directly to the battery and you eliminated this wire right here for the most part, it is still physically connected like that. All right, so tomorrow we will work on building circuits of multiple light bulbs and batteries.